There is a photograph that should not exist. It was taken in the summer of 2022 by a machine the size of a tennis court, suspended in darkness a million miles from Earth. The machine, the James Webb Space Telescope, had been pointed at a patch of sky so small that a grain of sand held at arm's length would have covered it entirely. What came back was not emptiness. It was this: thousands of galaxies, each containing hundreds of billions of stars, pressed together into a frame smaller than a fingernail held against the night. Some of them bent the light of galaxies behind them, warping it into arcs. And near the edge of the image, almost too faint to register, a small red smear, a galaxy whose light had been traveling since before our solar system existed, since before most of the stars you can see in the sky were born. That smear is 13.1 billion light years away. It is, in a meaningful sense, a photograph of the past. This is what telescopes actually do: not see across space, but see across time. Because light travels at a finite speed, observing something distant is the same as observing it earlier. The further you look, the younger the universe appears. Webb was built specifically to push that observation as far back as current technology allows, to collect light from the first galaxies, the first stars, the first moments when the universe became something other than a uniform, expanding fog of energy and heat. What it has found, and what scientists are still carefully trying to interpret, is not entirely what was expected. Before Webb returned its first images, cosmologists had reason for confidence. The broad architecture of the universe's origin, the hot Big Bang model, had survived decades of increasingly precise scrutiny. Not because scientists believed it on faith, but because the evidence had arrived from multiple independent directions and pointed to the same answer every time. The reasoning begins with an observation. The universe is expanding. Everything is moving away from everything else at a rate proportional to distance, a relationship first quantified by Edwin Hubble in the late 1920s and now known as the Hubble constant. The universe is currently expanding at roughly 80,000 kilometers per hour per million light years of distance, which means the further something is from us, the faster it recedes. If the universe is expanding now, it was smaller before. If you run time backward, the galaxies converge, the space between them closes, the density rises. Follow that logic to its conclusion and you arrive at a moment, approximately 13.8 billion years ago by current estimates, when all of the energy in the observable universe was compressed into a single point of infinite density and temperature, a singularity, from which everything we can see or will ever see eventually emerged. It was the Belgian cosmologist Georges Lemaitre who first proposed something like this in 1927. He called it the hypothesis of the primeval atom. Fred Hoyle, who opposed the idea, gave it its famous and somewhat dismissive name, the Big Bang. The name stuck, the idea proved more durable still. But how do you actually measure the age of the universe? The method is less mystical than it sounds. It requires making three assumptions: that matter is distributed uniformly across the universe on the largest scales, which appears to be true when you zoom out far enough; that the laws of physics operate the same way everywhere, which all available evidence supports; and that the expansion itself began everywhere simultaneously, rather than spreading outward from a single point in space. Given these assumptions and the known rate of expansion, a set of equations, rooted in Einstein's general relativity, connects how old the universe is to how it has expanded throughout its history. The age calculation draws on several instruments at once. The Hubble constant gives you the current expansion rate. The cosmic microwave background, a faint, uniform glow of microwave radiation visible in every direction of the sky, gives you a snapshot of what the universe looked like 380,000 years after the Big Bang, when it first cooled enough for atoms to form and light to travel freely. The distribution of elements, particularly hydrogen and helium, gives you another constraint, because the hot Big Bang model predicts specific ratios for how much of each would have formed in the first minutes after expansion began, and those ratios match what we observe in the oldest stars. 3 different methods using 3 different kinds of data arriving at the same answer: 13.8 billion years with an estimated accuracy of around 99%. This convergence is not nothing. It is in fact exactly what a successful scientific model looks like, which is why the anomalies, when they began to accumulate, were worth taking seriously. Before Webb, there was already one problem waiting quietly in the data. Roughly 200 light-years from Earth, close in astronomical terms, sits a star called HD 140283. Astronomers call it Methuselah. It is a metal-poor star, which in stellar physics means something specific. It formed before multiple generations of stars had died and scattered heavier elements into the interstellar medium. It is therefore very old. Based on its evolutionary state, the precise way it has consumed its hydrogen fuel, the slight changes in its internal structure that can be read through spectroscopy, astronomers have estimated its age at approximately 14.5 billion years, give or take about 800 million years. If that estimate is accurate, Methuselah is older than the universe's age. Or, more precisely, it is older than our current estimate of the universe's age. The error bars on both figures overlap. The star could be 13.7 billion years old, the universe could be 14.3 billion. So this is not, strictly speaking, a crisis, but it is a data point that sits at the edge of the model's comfort zone. A star that appears older than its origin is a quiet signal that something, somewhere, may need adjustments. Webb has since added a different kind of pressure to the age question, not through ancient nearby stars, but through the earliest galaxies it has observed. In early 2025, the telescope identified what is currently the most distant confirmed galaxy ever detected, MOMS Z14, a system whose light was emitted a mere 280 million years after the Big Bang. The galaxy is not just distant, it is large, it is luminous. It contains what appears to be a fully formed population of stars, stars that should not, by the model scientists had built, have had time to coalesce. This does not, by itself, disprove the 13.8 billion year estimate, but it suggests that the very early universe was doing things more quickly than the models allowed for, which means either something is wrong with the models, or the universe had conditions in those first hundreds of millions of years that we have not yet fully understood. When cosmologists designed Webb, they expected to see a sparse early universe, a protocosmos just beginning to organize itself, with scattered proto-galaxies assembling slowly under the pull of dark matter. What the telescope actually showed, as its data accumulated through 2022 and 2023, was something considerably busier. There were too many galaxies. They were too bright. The implication, if you took the brightness at face value, was that those galaxies contained far more stars than they should have had time to form. This was not a small discrepancy. It was the kind of gap that makes theorists sit with their models and wonder what they've gotten wrong. Some of the discrepancy turned out to have a mundane explanation, though one that illuminated something important. Researchers at the University of Texas, studying Webb's Cosmic Evolution Early Release Survey, realized that the excess brightness in some of those early galaxies might not have come from stars at all, but from the accretion disks of massive black holes at their centers. Black holes consuming nearby gas generate enormous amounts of light that, if not properly accounted for, would be attributed to stellar populations that are actually not there. When scientists factored in the likely presence of these feeding black holes, the inferred stellar masses dropped and the galaxies fell back into rough agreement with the models. Problem partially solved, but solving it introduced a new problem. Those black holes had to be there, large and luminous, near the very beginning of the universe, which raised its own question. How? Black holes come in roughly two sizes. Stellar black holes, the remnants of massive stars that have exhausted their fuel and collapsed, have masses anywhere from a few times to perhaps 100 times the mass of our Sun. They are well understood, their formation well documented. When a star of sufficient mass dies, it collapses. A stellar black hole remains. Then there are supermassive black holes. These are a different order of object entirely, masses ranging from tens of thousands to billions of solar masses, found at the center of most large galaxies, including our own. The Milky Way's central black hole, Sagittarius A, contains the mass of roughly 4 million suns. The question that has occupied cosmologists for some years is simple to state and difficult to answer. How did the supermassive ones form? And could they have formed fast enough to explain what Webb is seeing? Supermassive black holes present in galaxies that existed within the first billion years of the universe's history? The obvious hypothesis is that stellar black holes grew over time, accumulating mass until they became supermassive. This is possible in principle, but it runs into a constraint known as the Eddington limit. The Eddington limit, formulated by the English astronomer Arthur Eddington in 1920, describes a balance between two forces acting on matter near a luminous object. As a black hole consumes surrounding gas, that gas heats up and radiates intensely. The photons carry momentum, a small amount, but enough to exert outward pressure on the infalling material. At a certain threshold, that radiation pressure overcomes gravity, and the black hole's food supply is blown away. Growth stops or slows dramatically. Simulations have shown that growing a stellar black hole into a supermassive one within the time frame Webb's observations require would necessitate near continuous feeding at or close to the Eddington limit from the moment of birth, an implausible scenario in a universe where the supply of nearby gas is finite and intermittent. There is also the curious absence of intermediate mass black holes, objects in the range of hundreds to tens of thousands of solar masses that should, if stellar black holes gradually grow into supermassive ones, exist in abundance. They have been extraordinarily difficult to find. A handful of candidates exist, but the population that should be visible is largely absent. This has led some theorists to propose a different pathway: direct collapse black holes. In the early universe, when everything was denser and hotter, interstellar gas clouds may have been massive enough and compact enough to collapse directly into black holes, bypassing the stellar stage entirely. If this happened, supermassive black holes were not grown from small seeds, they were born large. This would resolve the timeline problem, but it requires conditions that no longer exist in the present universe, making it difficult, though not impossible, to confirm. In 2023, a black hole designated LID 568 drew attention for a particular reason. It appeared to be eating at 40 times the Eddington limit. LID 568 is located between 12.1 and 12.3 billion light-years from Earth, far enough that its visible light has been shifted entirely into the infrared. It required the combined power of the Chandra Cosmos Legacy Survey and the James Webb Space Telescope to detect at all. The galaxy it inhabits is barely a point of light, but the X-ray emissions from its accretion disk were legible, and they told a story that seemed to contradict established physics. If accurate, that accretion rate would have meant the Eddington limit was not a hard ceiling after all, at least not always, not in the early universe. There are theoretical mechanisms by which a black hole might briefly exceed it. If the outgoing photons are focused into narrow jets rather than radiating isotropically, the remaining directions can continue receiving infalling matter with less resistance. Or a particularly dense concentration of nearby gas might allow brief episodes of super Eddington feeding before the photon pressure catches up. Either scenario, if common in the early universe, might explain how supermassive black holes reach their observed sizes so quickly. The case of LID 568 was later revisited. Researchers Do-Hyung Kim and Myung-Shin Im, publishing in the Astrophysical Journal, reanalyzed the Webb data and concluded that dust obscuring the black hole had been underestimated. When corrected for, the true brightness, and thus the true accretion rate, fell back within normal bounds. LID 568 was not breaking the Eddington limit, it had only appeared to. The mystery remained. There is one final anomaly worth examining in detail, because it is both the oldest and, in some ways, the most precise. It concerns an element that most people encounter in their phone batteries before they encounter it in cosmology: lithium. To understand why lithium matters, it helps to understand what the hot Big Bang model predicts about the early universe's chemistry, a field called Big Bang Nucleosynthesis. In the first minutes after the universe began to expand, temperatures were high enough for nuclear fusion to occur. Protons and neutrons combined. The calculations, run with precision over many decades, yield specific predictions: approximately 76% hydrogen by mass, 24% helium, and trace quantities of a few light elements, including lithium. The predicted primordial lithium abundance is extraordinarily small, about 0.000007% of all matter by mass. But even that tiny predicted quantity is roughly 3 times higher than what astronomers actually observe when they examine the spectra of the oldest, most metal-poor stars, the ones that would retain the closest approximation of primordial chemical composition. The lithium is missing, not entirely, but significantly. 3 times too much was predicted. 3 times too much is not there. This is the lithium problem. It has been known since the 1980s. It has not been solved. A second, stranger anomaly accompanies it. Lithium-7, the most common isotope, appears in roughly the expected pattern relative to other elements, just at the wrong overall abundance. But lithium-6, a rarer and less stable isotope with 1 fewer neutron, appears in the oldest stars at approximately 1,000 times the predicted abundance. The model says it should barely exist. It is there. 2 possibilities present themselves, and scientists have been weighing them carefully. The first is that our observations are incomplete. Reading the lithium content of ancient stars requires interpreting spectral data with precision, and that precision becomes harder to maintain across cosmic distances. It is possible that processes within the stars themselves, fusion reactions or mixing events that bring material from the stellar interior to the surface, are altering the lithium abundance from what the star originally contained. If so, the primordial universe might have held the predicted amount of lithium all along, and what we are measuring is the residue after stellar chemistry has worked on it for billions of years. The second possibility is that the hot Big Bang model is incomplete. Not wrong, the successes of nucleosynthesis in predicting hydrogen and helium ratios are too precise and too consistent to this mess, but missing something. A process, a particle, a mechanism in the first minutes of the universe's existence that produced or destroyed lithium in ways the current equations do not account for. If true, it would not overthrow the model. It would extend it, which is how science typically works when it is working well. It is worth being precise about what all of this does and does not mean. None of these anomalies, not Methuselah, not the excess of early galaxies, not the presence of large black holes in the early universe, not the missing lithium, have overturned the hot Big Bang model. The model remains the best supported account of the universe's origin that exists. Its predictions for hydrogen, helium, the cosmic microwave background, and the large-scale structure of the universe are borne out by observation with a consistency that no competing framework has approached. But science does not require a theory to be overturned in order for it to be revised. What the accumulating anomaly suggests is that the early universe was more dynamic, more structured, and more complex than the models anticipated, particularly in the first few 100 million years. Galaxies formed faster, black holes grew faster or formed through different mechanisms. Something happened to lithium that the equations do not account for. Stephen Hawking, who had been one of the leading proponents of the Big Bang singularity, eventually softened that position. In A Brief History of Time, he wrote that quantum effects might require the concept of a precise singularity to be abandoned, even while the broad architecture of the theory remained intact. This was not a retraction, it was a refinement, which is what theoretical physics looks like from the inside. The picture is not wrong, it is unfinished. Consider what it means, physically, that any of this is knowable at all. The cosmic microwave background, that faint, ancient glow that permeates the entire sky, is the universe's oldest available image. The light it carries was emitted 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and for photons to travel freely. Before that moment, the universe was opaque. Light could not propagate. There is no older image to take because there is no light from that era left to collect. 13.8 billion years later, that light arrives at our detectors, stretched by the universe's expansion from visible wavelengths down into microwaves. And within it, in the slight variations of temperature from one patch of sky to another, variations of less than 1 part in 100,000, are the seeds of every galaxy, every filament, every void that exists in the universe today. The structure of the cosmos at 380,000 years became the structure of the cosmos at 13.8 billion years, and scientists can trace the correspondence. That is not a metaphor, that is a measurement. The anomalies Webb has surfaced, the bright early galaxies, the unexpectedly large black holes, the missing lithium, exist within this framework, not outside it. They are data points that the framework must account for, questions that the framework has not yet answered. But they are also, in a sense, gifts. Each anomaly marks a place where the current model does not fully describe reality, which is to say, each one identifies a direction in which understanding can grow. The universe began in conditions we can only partially reconstruct. It has been expanding, cooling, and complexifying for nearly 14 billion years. What we can observe of it, the galaxies, the background radiation, the distribution of elements, the ancient and distant smears of light that Webb collects at the edge of its resolution, is a record of that process, incomplete but coherent, legible to those who know how to read it. The lithium is missing. The black holes arrived early. Some galaxies formed faster than expected. These are not reasons to abandon the story. They are the story, the places where the story has not yet been finished. There is a particular kind of satisfaction available in working at the edge of what is known, not the comfort of settled answers, but the sharper pleasure of a question well posed, a discrepancy properly measured, a gap in the model clearly identified. The scientists who study these problems are not failing to understand the universe. They are doing what scientists do, narrowing the distance between the map and the territory, one careful measurement at a time. Somewhere in the universe, 13.1 billion light-years away, probably less than that, a small red galaxy drifts, unknowing. The light it emitted at its birth is still traveling. Most of it will never reach anything, but some of it reached us, was gathered by a mirror 6 times larger than Hubble's, passed through instruments sensitive enough to read its chemical composition, and told us something true about a time before the Earth existed, before the sun ignited, before the molecular cloud from which our solar system formed had even begun to collapse. That is what the telescope found, in a patch of sky smaller than a grain of sand.